Okay, so let me see if maybe I want to stop the video. So let's make sure that I sometime I experience the internet issues. I will just stop my video. So first of all, so welcome to be part of the NSFIU program at UTSA. So today I'm going to give quite a brief introduction to robotics. So I cover three main areas. One is the fundamental aspect, including the history, the key component of robotics, and I'll talk about some other component like how to do the modeling control aspects. I think that's also will be important. Okay. So during my presentation, if you have short question, you can just stop me, or you can type in the chat. I can answer your questions either when I do the presentation or after the presentation. Okay. Okay, so let's get started. So first, I will talk about part one will be fundamentals. What are fundamental in component robotics? And I'll keep on the second part and the third part after finishing the first part. Okay, the first one will be, okay, let me move this a little bit so I can see my screen well. So first one is, what is the robotics? What is robotics? So this is a definition from the Wikipedia. They call it a computer-controlled machine with some degree of freedom, which means you must have some degree of freedom. In other words, if you talk about sensors, they are actually static. We normally don't consider them as robotics, okay? And as the typical robot will include sensors, computational or computation, action, and human robot interaction. So humanoid that's optional component. You may not have that. Okay. So what the sensors do is to provide information about environment. For example, for the navigation, we have to see what's happening in the environment and try to avoid other obstacles or other objects in the environment. So you have to see that. The computation, what it's trying to do is to process data collected from the sensors. For example, you get image data from the cameras, and you have to process that to be able to tell what the environment looks like, and what you have to do later on, which is in the action part. The action is to accomplish desired goals based on computation from sensory data. So the goal is you actually want to do something, right? For do something, either you do, let's say you move the robot from one place to another, or in the manufacturing, you actually move the robotic arm from one position to another one. Okay. So human robot interaction talks about how we as human can interact with a robot using like command, maybe even programs. Okay. But this is optional. In certain cases, you don't have that one. Okay. So in other words, the three key components for robots include the sensing, mainly for perception, computation with localization, position, velocity, and also we do control action. We actually provide action for the robot, like control, planning, and replanning. Okay. Let me see why it wouldn't do. Let me run my slide. Okay. So the type of robots can be generally categorized into the following categories. They're not like exact categories. They're kind of other categories as well. But there's main types of robots, including mobile robots. We have ground robots, aerial vehicles, robots, and animal robots, basically. And also you have robotic arm. Typically they are stationary, but they have manipulators that can move, okay? For example, in the manufacturing or construction area, you have robotic arm that can move objects from one place to another without actually moving the robot itself, okay? Human robots has been pretty popular these days. Okay, they are like a human-like robot that can walk and climb. The DAPA, if you know the DAPA grant challenge, they have like kind of competition on human and robot that can actually operate like humans. Next one is micro robots. They are kind of tiny, small, kind of motivated by the biology, like the bird, other animals. Okay, they're kind of very small, but they're very efficient. Okay. The next one is autonomous cars. Autonomous, that's at least as a separate one because it's also considered as a mobile robot. The autonomous car has been really popular. You know, the Teslas as autonomous cars, they're really popular. So they are kind of involve much more intelligence and onboard computation than the traditional mobile robots. The next one is soft robots. It mainly means the robot can change its shape, color, type, whatever. So that's kind of very important, especially in the medical area. So like tiny small robot that can change its shape and type, and actually can treat kind of disease. That's kind of very one of the areas. The other areas that I've been working on is called soft actuators or robotic for the solar energy. So applications. Okay. So what robot can help us, right? You can ask, why do we want to use a robot? Okay, the robots have a few, typical application that are quite unique, for us. So, for example, the robots are really good at jobs that are kind of dangerous for humans. We don't want to use a human in certain situations which may be dangerous. For example, I believe this is an example showing that robot can be used for the sanitization. For example, in the COVID-19 situation, you can use a robot that actually do the sanitization or the cleaning of the stuff, for example, in the hospital. Also, robot can help us in repetitive jobs that are kind of typically boring, stressful, and labor intensive. For example, in the manufacturing or welding tasks, human can do it, of course, but human don't want to do it because it's kind of really boring and stressful. And as time goes on, people get stressed and they cannot perform the job as really well. Okay. Some other tasks the human may not want to do, for example, cleaning stuff, and typically people don't want to do, and we can use the robot, like the Roomba, if you know the Roomba that can do the carpet cleaning of the stuff for humans. So here's a brief history of the robot. Actually, it can be if you can see that can be dated back in like very early, like a few hundred years ago, in the almost 1500, right? So that's what started the sketch plan for the robot by that time, and actually get more more activity recently, like starting like 1700 to 1900, and to 1932, for example, the first true robot toy was produced in Japan, and also in like 54, the first program robot arm was created. So you can see a lot of more activity going on since then, because the computer actually becomes available, and also we have also a lot of advancement in kind of control in the computation in the hardware as well. And in 2004, Epson released a flying camera robot. That's pretty cool one, right? That's pretty small actually, size. In 2008, the first robotic vacuum cleaner was introduced. I think this is I don't know the brand, right? So this is like first vacuum cleaner was introduced. And recently, there are a lot of more activities, from like Tesla's autonomous car to the Boston Dynamics. If you know, they are designing the humanoid robots that can jump, pretty stable. Okay, so here's this chart shows the basic, like the market right now for robotics. So I got this data from the following. You can check the following web page about all other numbers. So I just list a few kind of numbers I feel kind of really interesting to share. So I read just a few, not all of them. So like they are now currently about 12 million robotic units worldwide in 2020, and the global spending on military robotics is set to reach 16.5 billion in 2025. And the number of robotics units sold in 2020 solely will rise to 265,000. So, and also there are kind of other numbers, like 88% of business worldwide plan to adopt robotic automation into their infrastructure. They either have done or they plan to do that. So North America itself, the business ordered about 31,000 robotics in 2020 only. Okay, so this slide shows a few of this, robotics that you could imagine. Okay, so this is like the Waymo, I think that's the autonomous car. This is the ABB robotic arm. This is a Honda humanoid robot. This is like the robot for Mars exploration. This is like soft robotics that can change its like hands like can grip and grab objects. This is like a very tiny robot that can actually for medical treatment. Okay. All right. So in terms of robotic hardware, they actually, roughly speaking, so I get this one. This is slides I get from another presentation and talking about the typical hardware for pneumatical kind of robotics. So they may not, some can may not be available, applicable to all other robotics, but that's the typical kind of hardware structure for robotics. So it lists as the power supplies, so typically provide the power for the robot to actually act, to move, for example. It has actuators, for example, motors. It has pneumatic air muscles, if you talk about the human-like robots, and has piezo motors and sensors and muscle wire. This is kind of connection between different components and electrical motors. That's what you can sort of imagine what typical hardware structure for a robot would look like. Okay, so here's a little more the software structure for the robot. This is pretty complicated. It's actually this is the X robot. What kind of structure software they are using. So you can see it's pretty complicated when compared to the hardware structure. Roughly speaking, you can see there are four kind of key components. One is called cognitive reasoning systems, perception system, application development, planning, and execution system. Okay, so the actual different functionalities within each kind of components. For example, in the perception system, we have object detection, which means you can actually detect object, and also human action recognition. So if we have humans interact with the robot, we want to detect what kind of action human can provide. For example, you can use a hand gesture to tell robot to move left and right, up and down, for example. And also it support like environment construction, like SLAM and object tracking. Okay, so I don't want to talk about too much detail about this one, but actually involve different at different levels and the different component I mentioned about the before, the sensing component and the control component, for example. Okay. All right, so the software architecture, get a little bit deeper into that. What kind of software architecture typically adopted by the robotics? The very general approach or very common approach is called a centralized control approach. So, which means we have a central processing unit or central processor, which can run on a central process for the planning. And we have other processes usually available to control motions and other type of sensors. I'll give example shown later on about the double grand challenge. They have the car talk about specific software, other stuff. So you get idea about what I'm talking about over here. So typically the centralized approach, you have a central reasoning mechanism. So it kind of as you can imagine, require reasonable process because you have to process all the data for the planning, replanning. So it should be powerful. And this also, I think, applied to the double grand challenge, the automobile I mentioned about in a few minutes or maybe 10 to 20 minutes. So usually this is good for static and slowing changing environment because you actually process a lot of data. It's not good for a real-time process, and it has high complexity. It's not very robust. Okay. And also you have second one is a human control. Okay, everything controlled by human. Okay, which is pretty obvious, right? In many cases. Synchronous, and also we talk about synchronous, reactive, and distributed. They are more about the mode that you can actually add on to the centralized control, even other control methods. Okay, so you have centralized, synchronized. You mean you control everything synchronously. Okay, asynchronous, you don't know what you don't want to do that. You can actually have planning, decision making, all those aspects they're doing on their own. They don't do that separately, individually. Reactive is more like you don't do pre-planning. You actually just do reaction, which means you don't plan something ahead of time. You just see something and you do take action. Okay. Also known as behavior control. And distributed one is more like local planning, reason, decision making, and actuation control. So the synchronous, I think you still can have a centralized one, but distributed means that you don't require, you don't need to have the complete knowledge. We don't have a complete knowledge of everything before we make a decision. Okay, so or like a planning, reasoning, or even the modern aspect. Okay. Okay, so let me see if I can move this up a little bit because it's kind of mission planning. I can go up. So mission planning. So typically when we have a robot, we actually talk about missions. So what they want to achieve. Okay. So the general idea is if I give some goals, how do we make the robot accomplish the desired goals? Okay. The couple of things that normally people use, one is rule-based planning, plan decomposition, and plan maybe provided by human controllers. Okay. As you can imagine, many cases, the goal robot is actually navigation is one important task because you want the robot to move from A to B. For example, for the, let's say, aircraft, even for the robotic arm, the most important task is for the robotic arm to be able to move object from one to another. So grabbing is one aspect, pick up the object and release the object at a certain location. That's kind of really important. So the navigation will be very important aspect of mission. So it's just moving from A to B. Okay, of course you have to pay attention to the environment. Okay. For mobile robots, they also manage some other goals or missions, including reconnaissance and monitoring, search and rescue, for example, in after disaster, or and also like the if for the military application, you can say I'm going from A to B, but stealthily, which means we don't want to be detected by someone. So we have some zones you don't want go to or try to avoid, try to stay stealthily, and also could be some other missions like the for the space missions as well. Okay. So for navigation from point A to B, so we typically consider a couple of things, including the obstacles. How do we avoid obstacles? And also terrain specification. So in certain cases, we want to optimize in terms of, for example, the time or the energy they used from A to B. So the terrain is pretty important. And also it's sometimes for safety issues, for some safety constraints. Also, we need to consider like environmental factors such as air current and water current. They're kind of important for not only for the low level control, you make sure that let's say for the aircraft, it should be stable. At the same time, they also can bring challenge in terms of, for the high level missions. You want to achieve from, let's say, from A to B within a given period of time. Then you try to avoid certain air current to be able to stabilize and move smoothly from A to B. Okay. Path planning is one important aspect to talk about before actually implement the algorithm. So path planning talk about what kind of path we will select. It does not mean that we will exactly follow the path, but path planning talks about a little bit high level, and we also have motion planning below that. Motion actually talk about exactly what kind of motion the drone or the aircraft should take or the robot should take to be able to follow the path. So typically the path planning, including you can just simplify it as like straight line. You move from A to B, let's say A to B, you can just divide into A to C, C to D, and D to B, for example. You can also follow curves. Follow curves, that's kind of important for the aircraft, especially for the non-holonomic robot. I'll talk about some kind of dynamics later on. The non-holonomic has a constraint. It's easy for them to move on the curve or circle kind of, not a straight line. Of course, straight line is fine. Follow curve, that's kind of more popular. Or like for wall following or wall tracing. Okay. Some other issues that when we do the planning is to consider like the planning horizon, like how much time we are planning ahead of time. If for long-term planning may be different from the short-term planning. Finally, is a fail-safe. The fail-safe including, for example, low batteries, and sensor failure kind of issues. What would happen in terms of planning if there's something wrong with the sensor? What would we do? Okay, sensor interpretation. So sensors are primarily used to ensure the vehicle robot is following a appropriate path, and also try to find an obstacle in the environment, just to avoid those. Okay. So for robots, the very typical sensors, including the sonar, the radar, and also cameras these days. So the old days, the sensor, sonar, and the radar, they're pretty popular because they don't provide like images. The image data are really more complex and not easy to process. Now, a lot of robots using the camera because the computational power becomes more popular. And also a lot of vision algorithms, computer vision algorithms, deep learning algorithms have been used to actually make this feasible. Okay. So outdoor robots typically using cameras and lasers. For example, the autonomous cars, they typically use laser and even LiDAR and with camera to actually detect environment. Okay. For a robot, especially for the air vehicles, the GPS, if you're operating outside, so the GPS is very important to know where it is. And also IMU, including the measurement of the position, velocity, acceleration, it's kind of important to make sure that it can avoid the obstacles. Okay. So the normal situation would be the robot need to interpret the input from multiple sources of data from different sensors. Okay. How do we perform the sensor interpretation? So, which means if you have a lot of images, we have a lot of data from LiDAR, for example. How do we interpret this data? So, a couple of ways that people normally do. We can do the simple neural network, kind of very popular these days. You can use fuzzy logic, and you can use a Bayesian network and hidden micro models, and also deep learning. Okay, that's become more popular. Because the sensor interpretation typically needs to be real time, especially for the operational robots. So we want to make sure that those approaches we applied won't be very comprehensive or very time consuming. Okay, especially for deep learning, it's very powerful, but it may not be applicable for online one. So we one typical approach that people have developed is to actually reduce or shrink the size of the deep learning modules so they can apply it for onboard processing. Okay, the other one is you can use a cloud actually to process the pre-processed data to get a good idea about the environment. Then you adapt that model to the changing environment. But that requires that the environment wouldn't change too much from the knowledge we actually trained in the cloud. So obstacle avoidance. So what would happen if obstacle is detected by sensors? So for mobile robot, like ground robot, for example, it can stop, replan, and resume. For example, it can stop over there and try to see if I'm going to replan again, not select the previous pass, and then start the process again. For the underwater vehicle and air-based vehicles, it may change the depths and altitudes because it has three-dimensional operational space rather than two-dimensional in the mobile robot. Although the opposite of typically is a low-level process, you just want to stop and replan, for example, it may impact the high-level process goals, meaning that replan at a high level may be needed. What I mean by that is it looks like you just need to avoid the obstacles, but in order to avoid obstacles, it may affect the high-level mission. For example, originally you plan the path from A to B, you think you can take A to another point then to B. Well, because there's an obstacle in between A and C, so it makes it harder to take that route. So it may be more worthwhile or more meaningful, more valuable to actually pursue another route. So that's what kind of high level you actually change your plan. Okay. We'll talk about the fail safe. So how do we handle the failure and also more importantly, how do we actually recover from the failure, right? So normally if a vehicle is not autonomous, the typical it may wait for new instructions. It's not autonomous because it's not human control. If something wrong, you can actually stop and wait for command from humans. If the vehicle is on its own, kind of autonomous, for example, is actually first to include the component to detect if there's any failure. If yes, if the goal, it will check if the obstacle is going to create any goal level planning to fail. If a failure is more severe than an obstacle, for example, the power outage, the sensor failure, like I mentioned before, the ultimate fail safe is to stop the robot and have it send out a signal for help. That's kind of what typical situation will look like. In other situations, for example, in the power outage, for the aircraft vehicle, the unmanned aircraft vehicles, it has to land and find location. It cannot stop there. So what happens is the the protocol will initialize to actually send the aircraft back to the home or the closest safe location. So now I'm going to one example is that's what I mentioned at the very beginning is the double grant challenge. This example showing the some good progress being made in 2005. I use the example because this is a pretty famous one. Is the double grant challenge road race. Okay, it's held in 2005. So the winning group is from Stanford. It's called Stanley. The name of the car, I believe, is called Stanley. So this is the car is based on Volkswagen Touareg four-wheel vehicle and a DC motor to provide the steering control, and linear actuator for the gear shifting, including drive, reverse, and park, and also includes a custom electric actuator for throttle and brake control. Wheel speed, steering angles are sensed automatically. So there are also a couple other sensors like the laser rangefinder, a color camera for long distance perception, and 2 radar sensors for forward sensing up to 200 meters. I believe this is image. Yeah, this image shows what the Stanley looks like. So you can see actually you have the top mounted sensors, lasers, is computer control mounted in the back of the on shock observers. You actually don't want this to kind of shot like more stable actually to remain stable, and actually to control the shifting and steering laser can find obstacle in a cone. Actually, you can find the obstacle in front about 25 meters in front of this the car. Okay. So the Stanley software, there's no centralized control. It doesn't involve centralized control. Instead, there are about 30 modules to handle each subsystem in parallel. So as you can imagine how complicated the system would be, the sensor data are time-stamped and passed on to the relevant modules. You basically do the real-time processing and try to process that as soon as possible, and also try to connect different sensors together to identify environment to actually make a decision about what actions, what routes should take. Okay. The state of the system is maintained by local processes, and that state communicate to other modules as needed. So the environment state is broken into multiple maps, including the laser map, vision map, and radar map. The health of individual modules, including the software and hardware, are monitored so that modules can make decisions based in part on the reliability of information coming from each module. So actually, each individual modules, they have the health monitoring to make sure the software and hardware are working correctly. So make sure there's no failure. If there's a failure, it will report it to corresponding component to make sure that action can be taken to address the issue. If not, the car has to stop. So the sensor data time processing, the sensor data time typically stamped and stored in the database of coordinates and forwarded. Perception layers maps the sensor data into vehicle orientation, coordinates, and velocities. The control layer regulates the actuators of the vehicle. So high levels, including the user interface and also communications. Okay, this will be high level stuff. Okay. The sensors, the laser used for the terrain labeling, including the obstacle detection and lane detection orientation. So it doesn't involve different levels, of course. The lasers can detect the obstacle at a maximum range of 22 meters, which is sufficient for them to avoid the obstacle if traveling no more than 25 miles per hour. Okay, and also in 2005, the map has been given before the competition was started. So actually, so they know the map exactly. Okay. The path planning. So prior to a race, like I mentioned, DAPA supplied all team with a file of the path. This will eliminate the need for global path planning from Stanley because you can actually plan the path. There's no other vehicle on the road. Okay. What Stanley had to do is to local obstacle avoidance, road boundary identification to stay within the roadways, and maintain a global map and provided added by GPS to determine where it is right now on the race. Okay. Perform path smoothing to make sure the turns are doable and match the predicted road coverage to the actual road. Because it move too sharply or it's not as desired, so the replanning or the motion planning has to be has been redone to actually let the card perform the desired action. Okay. Okay, so high level planning, Stanley only goal was to complete the race course in minimum time. So the gold standard is to finish the task in minimum time. Also, Stanley would drop out the automatic control into human control if needed. Okay, or if we start by commanded by DAPA or the commander. So here's the typical information for the what the race is about. So the race was approximately 130 miles in the desert terrain that included wild level spans, narrow and slanting and rocky areas. So it's kind of not very easy to, even from the control perspective, it's not a actually on a typical road that we'll see for our cars. Even for the autonomous cars, it's relatively easy because they do not have those different terrains. So 2 hours before the race, team will provide the race map at about 2935 GPS coordinates and social speed limit for different regions of the race. And Stanley is which wins the competition, actually complete race in just under 7 hours, and the average speed is about 9.1 miles per hour, and the maximum speed is 38 miles per hour. And a total of 195 teams registered and 23 raced, only 5 finished. So it's very difficult to actually accomplish the task. Okay. Okay, so that's the example I talk about the one. I hope give idea about how complex this would be. Okay, so even if this is 2005, and these days, I believe right now, the autonomous car can be very much better than the Stanley, I believe. For the Teslas, for the Uber, other autonomous cars, they become more capable than the Stanley was like 15, 16 years ago. Okay. All right. So as a matter of fact, what is the typical goal? What is the goal for the robot, right? Where should we go? Okay. The main goal that, at least from my understanding, is the robot we want a robot to actually work like humans. In other words, we want a robot actually to, like the autonomous car, they can move like they can work as humans. When we drive a car, if we have trust on a robot, the robot has to act like us. Okay, so we call it human-like robots because they perform like humans and we can trust them. Okay, so they are still a long way ahead of that to develop or design a robot that can work like humans. So they're having, so here I'm showing a video which is not about a robotics car or autonomous car, the car I mentioned before, but actually showing about what has been made or what kind of issues that people face with, what kind of challenge you will see, like when we want to develop human-like robots. Okay, there's still a lot of challenges. Okay, so I'm going to play this video showing this also DARPA Grand Challenge a number of years ago that used developed like the human robot that can actually walk, step off the car and open the door, for example. As you can see, it's not easy to achieve that. I'm going to run a video. After that, we're going to talk a little bit more. Okay. Okay, so as you can see, this is like 2005. So it's a competition. I think also DARPA Grand Challenge. So well, by that time, there's not too much, a lot of progress. You can see a lot of issues over when we actually have the robot actually climb the steps, try to step off the car, for example, try to find the knob, open the door. It's not that easy for the robot to actually do that. So a lot of progress to be made if you know Boston Dynamics actually have developed have make a lot of progress towards human-like robots. Okay, but they still have a lot of challenges. Okay, I'm gonna look at the next one. So first of all, how do we achieve human level responses? So we can normally we can do the basic control and planning. For example, you can move up and down. And now I believe for the robot, they are good at, if they're obstacle, for example, they can jump, do all this kind of basic maneuvers, but they are not very good at high level responses. Normally they're pretty slow. Okay. And also how do we achieve human level reasoning? For example, not just the past planning and obstacle avoidance. That's more like does not involve a reasoning. So humans are good at understanding and reasoning. How do we actually equip this robot with high level reasoning that we can do? Okay, and so past planning obstacle avoidance that really done really well at this time, and mission planning is possible, which means they can plan the mission. You can do the A star or different arrows and actually plan the path, do the motion planning, which is pretty good now. Okay, but for complex mission reasoning, it's kind of difficult. Okay, especially when we face, for example, when we face multiple objectives, we want to achieve both A and B and C objectives, and we have a good idea of how to balance those. But it's not easy for robot to actually understand how to balance those objectives. Okay, so the ultimate question is, there with the advancement of a lot of progress made in the AI, artificial intelligence, what can AI offer? Okay, so there have been a lot of work on the robotics. I would say this: robotics is such a interdisciplinary area that people from different areas can actually contribute, including from the hardware side, the sensors, the computational side, the control side, algorithm, from the computer science, and also AI, especially in AI. I think AI can bring a lot of this tool that can help the traditional planning, traditional control, traditional data processing, for example, to actually achieve much higher accuracy, and also in terms of modeling and also control. Okay, and also even in the mission plan, the reasoning aspect, AI can provide a lot of tools that we can use. Okay, those are more like open, because I don't know what other. I don't want to talk too much about the technical aspect in terms of AI. But for the general introduction AI, I believe we have another short course on this, and also we have specific we have also short course on specific topics on like the CNN, the LSTM model. I don't want to talk about those one over here, but I just give idea saying that AI can potentially provide a lot of tools for us to use to achieve human-like robots. Okay. All right. I'm not sure if you want to stop a few minutes, or should I continue?
Maybe we stop a little bit. It's about 40 minutes right now.
Okay. Okay. I think we can stop for 5 minutes. That's okay.
Okay, I'm going to stop recording
Okay.
right now.
Okay.